Hello students, in today's video we will learn about the fundamental interactions of nature. So there are four fundamental interactions in the physical world, and these are electromagnetic interaction, weak interaction, strong interaction and gravitational interaction. So we will look into the properties of each of these interactions. First of all, electromagnetic interaction. As you might already know, the electromagnetic interaction is associated with electric, magnetic and optical phenomena. So you might know that like charges repels and opposite charges attracts due to the existence of electric fields, right? So the interaction between these charged particles and the electromagnetic radiation and all these are determined by electromagnetic interaction. Now we have learned about the electromagnetism and we have learned about how Maxwell unified electricity and magnetism, and later optics was also merged with this electromagnetic theory. So electromagnetic interaction studies the interaction between various electric, magnetic and optical phenomena through the electromagnetic radiation and so on. The forces that exist between these charged particles, these magnetic particles and various optical or other electromagnetic radiations are studied under electromagnetic interaction. Now for this electrodynamics, for this electromagnetic interaction, there is a quantum field theory as well, the quantum electrodynamics. And according to quantum electrodynamics, these interactions between charged particles, for example, the repulsion or the attraction between charged particles, are all due to exchange of photons. So you might know about photons, right? Photons are the quanta relating to electromagnetic radiations. They are the quantum particles of EM waves. So according to quantum electrodynamics, photons are responsible for the electromagnetic interaction. Charged particles interact through exchange of photons, and they are the quantum particles associated with electromagnetic waves, EM waves. So when we say about radiation or electromagnetic wave, photons are actually being propagated. That is what is being proposed in quantum electrodynamics. So this is about the first interaction, electromagnetic interaction. Now the second type of interaction is the weak interaction. So this is a kind of nuclear force or a force that exists within the nucleus. This interaction, this nuclear interaction is responsible for a type of radioactivity known as beta decay. So what is beta decay? It is a nuclear reaction in which electrons or positrons are emitted from the nucleus. The weak interaction is involved in this kind of beta decay process. This interaction is very weak when compared with other reactions. So that is why it's also called weak interaction. It's a weak force that exists during the nuclear reactions, like in the case of a beta decay. So this is a beta decay that is being depicted here. A nucleus will be emitting positrons or electrons to attain stability. That is the beta decay process. And weak interaction is the force that is involved in these kinds of reaction. Now three scientists, Sheldon, Glashow, Abdus, Salam and Steven Weinberg, tried to propose a new theory, a unified field theory combining, so unified field theory combining the electromagnetic interaction and the weak interaction. So EM interaction and the weak interaction can be combined under the unified field theory or electroweak theory. And according to this proposed theory, weak interaction is mediated by two charged W particles and one neutral Z particles. So three particles, W plus, W minus and Z particles are involved in the weak interaction process. That is what is being proposed under the electroweak theory. So as indicated here, W minus particles carries away the negative charge and transforms the electron to an electron neutrino. Similarly, Z0 particles transforms neither charge nor mass. So these particles are directly involved in the weak interaction process, and the proposal of these particles helped in developing the electroweak theory. Now coming to the third interaction, which is the strong interaction. So this is also a nuclear force that is experienced within the nucleus, and this strong interaction is responsible for binding of neutrons and protons inside a nucleus. And also we have learned that each nucleon within the nucleus is composed of smaller particles called quarks, right? So these quarks are held together within the nucleon due to this strong interaction. So we can say that the strong interaction binds quarks inside the nucleon, and the residual strong interaction binds nucleons in the nuclei. So this binding together of various fundamental particles and proton and neutron are mediated through this strong interaction. Now this theory also has a quantum variation called quantum chromodynamics. According to quantum field theory or the proposed quantum chromodynamics, this force between these particles is proposed to be due to an exchange of particles called gluons. So before coming to gluons, let us understand the term chromodynamics. Just like there are two kinds of charged particles, positive and negative, according to quantum chromodynamics, the quarks can have three different colors: red, blue and green. So this does not have to do anything with the real color that we see around. These are three basic properties that the quarks can have. And this dynamics between quarks, depending on its color, red, blue or green, is actually studied under quantum chromodynamics. And these quarks interact through the exchange of gluons according to the quantum chromodynamics. The force between quarks is due to the exchange of a particle called gluon. And another interesting aspect of this force is that as distance between quarks increases, as r increases, the force between the quarks also increases. And hence it is very difficult to separate any two quarks, and that is why we do not see any quarks in its independent form. We normally see protons and neutrons as a whole, right? We cannot separate a quark from inside the proton. The reason is that this strong interaction is very strong. This is the strongest of all four interaction, and they binds all the quarks together. And if we try to separate any particular quark, the force will further increase, making it very difficult to separate a quark. Now this force is also responsible for holding the nucleus together as well as holding the quarks together within each nucleon. Now there has been some attempts to unify this strong interaction with the electroweak theory. So we have strong interaction, we have weak interaction, and we have electromagnetic interaction. Weak interaction and electromagnetic interaction were already unified under electroweak theory. Now there have been attempts to merge this strong interaction with the electroweak theory to develop a new theory called grand unified theory. So this grand unified theory tried to predict proton decay, and they proposed that the life of the protons will be of the order of 10⁻32 years. But this grand unified theory was not able to develop into a full picture. There have been many differences between the experimental results and the theory, but still there are attempts going on to merge this strong interaction with electroweak theory. That is, we are combining three forces: one, the strong interaction; second one, the weak interaction; and the third one, the electromagnetic interaction, into a single force or single interaction, and that is actually studied under grand unified theory. Finally, coming to the fourth interaction, the gravitational interaction. This is the weakest of all interactions. You might know about gravitational interaction. This is the force that is experienced between any two bodies having mass. And Isaac Newton was the first person to propose this law of gravitation. So as you can see, if there are two bodies with masses m1 and m2, there is a gravitational force existing between them, and it is given by g m1 m2 divided by r square. That is, the force is proportional to the product of the masses, and it is inversely proportional to the square of the distance between them. So this was proposed by Isaac Newton. Now in the year 1916, Albert Einstein developed the general theory of relativity. And according to this theory, a complete new picture about gravity is obtained from this theory. So this general theory of relativity was a combination of special theory of relativity and Newton's law of gravity. So special theory of relativity plus the gravitational laws yielded the general theory of relativity. And according to this theory, the gravitational force is experienced due to curvature of space-time. So as you can see here, suppose say our Earth is placed in the space, and the mass of this object, Earth, will cause curvature in the space-time, and these curvatures are actually responsible for the gravitational force produced by Earth. That is the concept that is proposed by general theory of relativity. Just like if you put a massive ball on a paper, this paper will be folding in the third dimension. Similar to that, any massive objects, Earth or any smaller objects that is placed in the space-time will be bending this space-time and producing curves in them, and these curvatures are responsible for the gravitational force. That is what is being proposed by the general theory of relativity, and the gravitational interaction is due to this intrinsic curvature of space-time. Now this theory proposed by Albert Einstein was quite successful in predicting phenomena such as bending of light. If the space is bent, the light will also bend through that space, right? Similarly, the precession of perihelion of Mercury. This was an experimental observation that was made, that the perihelion of Mercury actually precesses around a particular point, and the explanation to these kinds of observations was given by the general theory of relativity. So it was quite successful theory in explaining many of the unexplained phenomena of the nature. And later, Albert Einstein and several other scientists worked hard to formulate a unified theory combining all these four interactions. So they went beyond the four-dimensional space-time and looked into higher dimensions in order to come up with a theory that actually combines all these four interactions. Earlier we saw that the grand unified theory tried to merge three of the interactions, the strong, weak and the electromagnetic interaction. Now there are attempts to merge or combine all the four interactions, including the gravitational interaction. And one such attempt is the theory of everything. Here the physicists tried to unify all the four interactions to a new theory under theory of everything. And under this theory, all the particles are assumed to be composed of small strings. So even the fundamental particles are composed of further smaller strings, and the interaction between these strings are the reason for all the forces and interactions that we see around. So this theory is also called the string theory or the superstring theory. So under this theory of everything, we are trying to unify all the theory of all the interactions and trying to bring out a simple picture for all the physics of interactions that we see around. So these are the basic concepts about the interactions of various particles, or the four fundamental interactions that we see in the physical world. So we have gone through the electromagnetic interaction, which is the interactions that is experienced by electric, magnetic and optical related particles. Then weak interaction associated with the beta decay process. The strong interaction, which is the force experienced within the nucleus and which binds the nucleons together. And finally, the gravitational interaction. So these are the four fundamental interactions. I hope their characteristic features are clear for you. Thank you.